All right, we're going to take a couple of minutes before we move on to section 10.8 and look at this. It's on page 584 in your text, converting areas and volumes. It's a topic that is often misunderstood with students. So if we, I'm just going to give you two examples. You can look at the other examples in the book. If we had 10 square yards and we wanted to convert this into square feet, how would we do that? Well, we'll start here with our 10 square yards, and we're going to multiply this by a unit multiple. Remember, a unit multiple involves the two units that we have there in an equality statement. So I hope you know that there are 3 feet in every yard. So I'm going to write either 3 feet per 1 yard or 1 yard in 3 feet. Those are both called unit multiples. Well, if I want to get rid of the yards and end up with feet, I want yards on the bottom to cancel this yard here, and I want the feet on the bottom. So I will use this form of the unit multiplier. So I'm going to say there are 3 feet in every yard. Well, notice that we have 1 yard here. We have yards squared here. That means yard time yard. So when you have a square, you actually have to multiply by the unit multiplier twice. So we need to put this in here again. Your book shows this a slightly different way, but this seems to make sense to me. So yard times yard is yard squared, cancels with the yard squared. And now we just multiply our numerators. 10 times 3 is 30. 30 times 3 is 90. We have 90 square feet. And we've converted from square yards to square feet. I'm going to do one more. We're going to look at cubic. What if we had 350 cubic centimeters and we wanted to know how many cubic meters would that be? So I have to find a unit multiplier. Well, first we can write what we have, 350 cubic centimeters, and then a unit multiplier that involves centimeters and meters. I hope you know that there are 100 centimeters in every meter. Or, we can flip it, 1 meter for every 100 centimeters. And then which one would we use to multiply here to get rid of centimeters? Would we multiply by A or would we multiply by B? I hope you all said B, because we want meters left, so that's going to be on top. We want the centimeters on the bottom to cancel with these centimeters here. Remember, this is like 350 over 1. All right, since we have cubic, how many unit multipliers do you think that we're going to need? Back here for square, we needed 2. So for cubic, we need to do it 3 times. So we're going to have a 1 meter per 100 centimeters. We're going to do that again and again. And then now notice in the bottom we've got centimeters, 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 which is the same as centimeters cubed. So those have been canceled, and I end up with meters, 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 which is meters cubed. And then if I multiply my numerators, I would get 350. I'm going to do it right here because you're going to see that we're able to cancel this a little bit. 100 times 100 times 100. I hope you all know the shortcut for this. 1 times 1 times 1 is 1. And then count up your zeros. 1, 2, 3, 4, 5, 6. That's a million, right? And then how could we simplify? I could do this. And actually, we could go in, if we wanted to leave it as a fraction, I could divide this by 5 and divide this by 5. But I'm going to do this instead. I'm going to write this as a decimal. So do you know what 35 divided by 100,000 is? Here's your decimal in 35. For each 0 in the bottom, I'm going to move the decimal place 1 to the left. So I got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is going to be 0.000 0.035 cubic meters. That is 35/100,000th of a cubic meter. All right, so I'm going to assign you a couple of problems from that section because it is so interesting. And moving on to section 10.8, volumes of pyramids and cones. If you remember, pyramids go to a point. Cones have circular bottoms and go to a point. And I think this is just the most beautiful thing. I don't know why it's true, but if something goes to a point, it's exactly 1/3 the volume of the prism or the cylinder that has straight sides. It's 1/3. So if you had a prism with an area base B that's the same and the same height, but this one goes to a point, it's a pyramid, you would be able to fill this up 3 times and dump it in, and it would completely fill that cube. Pretty cool. So the volumes of pyramids and cones is simply 1/3 big B, which is the area of the base, times the height. And all the rules about the area of the base that we learned before go here also. All right, let's take a look at example 1. The base of a pyramid is a square, so we got a square base pyramid. The side lengths of the square is 24 feet, and the height of the pyramid is 9 feet. Find the volume of the pyramid. So since it's a pyramid, volume is equal to 1/3 area of the base times the height. Its base is a square with a side length of 24. So the big B is going to be 24 squared, and the height is 9 feet. So we simply put those numbers into a formula, multiply it out, and the volume would be 1,728, what are we talking about? Cubic feet. So you could always put feet with a little 3 there. Now, just a little side note, when you're doing your homework, I want to see all of this, please. Remember, it helps you learn the formula. If you write the formula first, then you substitute in the numbers specific to the problem, and then do your arithmetic. Show me all those steps, please. Here's example 2. Find the volume of the cone. So volume is equal to 1/3 pi r squared h. If you're given the diameter, you need to have that. So half of 13.5 is 6.75. Remember that our big B here, since it's a circle, is pi r squared. So we've got 1/3 pi, here's the radius squared, and then from the diagram we see the height is 10. Do the order of operations, multiply it out, you get about 477.1. Okay, we can also have some more interesting problems. I love these where there are 2 shapes kind of put together. Here's a grain silo is composed of a cylinder and a cone. Find the volume of the silo to the nearest cubic foot. So what we need to do here is break this into 2 parts. First, we have a cylinder. Remember, if it's got straight sides, we have the area of the base times the height. So let's stop and do that. So the area of the base is going to be pi r squared. If you're given the diameter, you can't work with that. You have to have that. So if the diameter is 18, the radius would be 9. So we have pi r squared h. And there's the volume of our cylinder. Now let's go to our cone. Again, pi r squared, the area of the base, pi r squared, times the height of the cone, which is given as 7, but since it goes to a point, 1/3 of that. So when you multiply that out, you get 189 pi. Now here's an interesting thing. If you have both values in terms of pi, you can add those together. It's like 2,349x plus 189x would give you 2,538x, in this instance pi. So you could leave it like this would be exact, but if it's a word problem with a diagram, it's a real thing, we usually slip in 3.14 for pi, and then find this to the nearest cubic foot. So I hope that you have some enjoyment with those. I will see you next time.